And hello everyone, and I will be presenting on the erosion subproject. I'll just share my screen and load up my presentation now. So that should all be coming through. Okay, so the subproject that I'm going to be speaking about focused on erosion and the improved understanding and management of erosion with LiDAR. So in terms of the presentation, I'll be just looking at an outline of the scope and the existing erosion models in the region, then just giving a brief summary of the LiDAR coverage and the digital stream network we generated from that coverage. Then an outline of the data collection we've undertaken to support the modelling, and a description of the upgraded models, followed by some brief messages at the end. So in terms of scope, the purpose of our work was to upgrade these regional erosion models, specifically the landslide susceptibility and ZNZ models, using the higher resolution LiDAR-derived topographic data. And alongside this, we were planning to undertake targeted acquisition of new erosion data to support the modelling. And so the outputs from this work are a set of upgraded models and layers that have been improved through the use of new data and model parameterization and the use of the high resolution topographic data from LiDAR. So just to give a bit of background first, there were several existing models in the region that we were focusing on. The first was a landslide susceptibility layer that was developed and supplied to Hawke's Bay Regional Council in 2020. And this is based on modelling that we developed as part of our Smarter Targeted Erosion Control MB program, and some work was published in 2021. Now, specifically, landslide susceptibility is all about understanding the spatial probability of future landslide occurrence given environmental conditions. So it's referring very much to the question of where landsliding is likely to occur rather than when. But the point here is it's a data-driven approach using statistical methods to look at where future land instability is likely to occur. And to do this, we need a number of different data sets comprising both landslide data from mapping, non-landslide locations, as well as a bunch of spatial covariates that could influence where landslides are more likely to occur or not. So using an earlier approach based on the national 15-metre digital elevation model, we produced a region-wide 15-metre resolution shallow landslide susceptibility layer for Hawke's Bay. And this used both a probability and a class-based scale, and you can see a zoomed-in example here where the yellow points are mapped landslides, and the colour coding indicates areas of higher and lower susceptibility. Now, the purpose of this really was to, again, assist in the council in thinking about where to target tree planting. And to my knowledge, that's been being actively used. But of course, the capture of LiDAR presented opportunity to improve on this. Now, in addition to the landslide susceptibility layer, we had also provided ZNZ erosion sediment load modelling to Hawke's Bay Regional Council. Now, this was provided a number of years ago, but was updated in 2020, specifically in relation to the riverbank erosion submodel. Now, ZNZ is a spatial model that predicts the average annual suspended sediment loads across the digital stream network. Now, in the pre-LiDAR state, ZNZ uses the River Environment Classification digital network, and it predicts suspended sediment loads for each segment in that digital network. But it does so by representing the different erosion processes that can contribute sediment. And you can see those here. So that includes surface erosion, landslide erosion, gully, earth flow erosion, and riverbank erosion, whilst also accounting for storage in lakes and deposition of floodplains. So it's what we call a sediment budget model. And basically we're computing a sediment budget for each watershed draining to each stream segment across the entire region. And it's the only erosion process-based sediment model designed specifically for New Zealand and parameterized with local data. So, as Ashton mentioned, the capture of regional LiDAR presented opportunity. Now, for our purposes, given we're focused on the catchment erosion sediment load modelling, we need complete catchment coverage. And the initial Hawke's Bay LiDAR survey didn't provide that. So to get complete coverage, we had to extend the existing, or the survey from 2020 to include areas in the upper Mohoka and Wairoa catchments, so those areas there. And that was fine because we already had access to the Gisborne LiDAR survey for that missing area, and we were able to access some data from the Waikato survey to fill the Mohoka area. So we basically, from that combination of surveys, we're able to produce a 5-metre DEM digital elevation model that is the basis for most of our modelling that I'll be describing from here on. Now, one of the first key steps in terms of catchment erosion sediment modelling is to generate a digital stream network, because this is essentially the spatial framework upon which we base the modelling. So as you can see here, in this zoomed in section, there's a comparison of the LiDAR DEM and the REC2 digital network. And I guess the key point to note is that the streamlines generated from the LiDAR derived DEM better capture the actual planform of the channels. So they better represent that sinuosity, which is a good example illustrated in this figure. And that's really quite important when it comes to thinking about riverbank erosion, for instance. So these are areas where you can see a marked improvement in the spatial data available for modeling. So the digital network that we generated for our purposes was based on 10 hectare initiation threshold, and that produced a total length of channel of just under 40,000 kilometers, which is considerably more than what was represented in the REC. And a large part of that is due to that sinuosity or the wiggliness of those streamlines, as well as the difference in the initiation threshold. In any case, having generated this network and undertaken a manual refinement process, it was then the basis for our modeling. So that combination of stream segments and then the watersheds draining into each segment provides us with a method or a framework to undertake the sediment load modeling in SedNetNZ. Now, moving on to data collection. As you can see here, we've got an example of landslide mapping. Now, for shallow landslide susceptibility analysis, we require data, and specifically, we need spatial information on where landslides have occurred. And we need to undertake this data collection in areas where we have overlapping coverage with LiDAR. So our focus was obviously on Hawke's Bay in the first instance, but we also augmented that data with data from other areas for which we'd had previously undertaken mapping and for which we had LiDAR coverage. The key here is you need high resolution aerial satellite imagery to do this well, because you need accurate spatial information on where landslides have occurred, and particularly the source area in this case, because we're focusing on susceptibility to failure. And so we were able to assemble a large inventory of landslides. That was the basis for the modeling of susceptibility. We're also interested in collecting additional erosion data to support the improvements in SedNetNZ. And one of the key areas we focused on was related to riverbank erosion. And this is possible because of the repeated aerial imagery captured across the region. And this allowed us to map river channel change over about a decade and look at areas that eroded or areas that are deposited, and basically compute that change at the stream reach or segment level across the region for the areas we mapped. And you can see here examples of change. So we mapped over 420 kilometers of channel across Hawke's Bay, and we augmented this data with another 380 odd kilometers of data from the Greater Wellington region, which we also had LiDAR for, so as to build up quite a substantial database for use in modeling of riverbank erosion. Now, in addition to understanding riverbank erosion, we also needed information on bank heights. And so to do that, we basically used the LiDAR data directly, in this case, the 1 meter DEM, and we selected a number of reaches spanning a different range of stream orders and hydrological conditions to look at the spatial variation in bank heights. And so we ended up mapping over 10,000 banks manually, and then summarizing this bank height information per stream reach or stream segment. And again, this is fundamental data to use in the sediment load modeling. Now, moving on to the model upgrades. So focusing firstly on the shallow landslide susceptibility model. So our previous model was based on the national DEM 15 meter resolution. It was based on a data set of 56,000 landslides, and the model performance was reasonable at the time. The numbers you can see there, AUC refers to the area under the curve, and it's a metric basically related to predictive performance. Value of 0.5 is essentially no better than a random guess. Value of 1 is perfect classification of landslide or non-landslide points that are fed to the model. Now, as you can see with the upgraded model, we're seeing very significant improvement. We approximately doubled the number of landslides available for modeling, but we saw a step change in terms of predicted performance as represented in the AUC there over 0.9 and accuracy of 84% in terms of classifying landslide and non-landslide points. And typically an AUC value of 0.9 is considered excellent in terms of model performance. Now, spatially, you can see quite a distinct difference of what this looks like when you zoom into an area. The key point to note really is that with the lower resolution based model, it's less able to classify land as either stable or unstable. What we really see in terms of the spatial representation is a better discrimination of areas that are likely to fail versus those that are likely to remain stable. What you're seeing there is landslide susceptibility using the previous model and the upgraded model based on land cover at the time, 2018 LCDB version 5, and it really highlights that improved discrimination of susceptible versus less susceptible areas. And so we're quite pleased with the outcome, and it really highlights the benefit of that higher resolution and more accurate topographic data for this type of modeling. Now, moving on to SedNet-NZ, we undertook a number of upgrades to the model. Ultimately, we couldn't do all the things we might like to do, so we had to focus on areas where we felt there was greatest value and effort and potential benefit in terms of the model outcome. So we focused primarily on the shallow landslide surface and riverbank erosion submodels, as well as the representation of floodplain sedimentation. There were no changes made to the gully and earth flow submodels. Basically, there's insufficient new data to justify further changes, although we have some work in the pipe that may in time allow us to make future improvements to these submodels. But ultimately, based on previous modeling, those three processes, so shallow landslides, surface erosion, riverbank erosion, contribute most of the sediment in the region. So the types of improvements we undertook, they basically involved integrating either new data into our modeling, or in the case of shallow landslide erosion, it involved incorporating our landslide susceptibility model into the landslide erosion submodel to improve the spatial predictions of landslide erosion. Susceptibility doesn't tell us about erosion, it doesn't give us a yield, but it gives us a spatial probability related to the likelihood of failure. And so we've incorporated that information with the submodel to predict erosion rates from shallow landslides. For surface erosion, we replaced the USD with the revised universal soil loss equation, so it's now fully implemented based on LiDAR-DM. And for the riverbank erosion, as I mentioned, we had a new data-driven approach, which I'll talk about further. And obviously with the floodplains sedimentation, we're now better able to utilize the LiDAR-DM to identify those low-lying areas that are likely to receive sediment if flows go over bank. So looking a bit more in detail now, I mentioned we integrated the new landslide susceptibility layer with the landslide erosion submodel. So basically this involved replacing what was a pre-existing layer called the erosion terrains layer, which was a class-based layer that was low resolution based on expert judgment of terrain susceptibility. Well, that's been replaced with this 5-meter resolution shallow landslide susceptibility layer. So we're now using a digitally based, high-resolution, data-driven method for identifying areas that are more likely to fail versus those that are less likely. However, as I said, we need to get information on the quantity of sediment generated by landsliding, not just the likelihood of a failure occurring. And so to do that, we updated the relationships we use in the existing SedNet-NZ model, but now applied using high-resolution digital elevation models. So these relationships relate to the total landslide eroded area versus slope. And basically, this is data derived from multi-decadal mapping from aerial photography, looking at the total area affected by landsliding through time and how that varies with terrain. So in the previous modeling, it was just a single relationship based on soft rock terrain. That's now been updated where we've got two relationships looking at landslide area versus slope, both for soft and hard rock terrain. Unsurprisingly, you can see a considerably higher total landslide eroded area per slope under soft rock terrain, as we'd expect, compared to hard rock, and a difference in the peak. Now, these data allow us to basically estimate average annual suspended sediment loads from landslide erosion. So essentially, we're saying that we have this accumulated area over many decades affected by landsliding, and how does that average out per year? It's not saying that there's landsliding every year, but that rather if you distribute that load across time over many decades, what does it contribute on average per year? And so the end result is an updated raster-based layer that expresses the yield of sediment from shallow landslides at this higher resolution than was previously possible, using these new data that have been updated in combination with high resolution topographic data from LiDAR. Now, in relation to riverbank erosion, we made a number of improvements here as well. And basically the focus was essentially to shift towards a more data-driven approach to utilize the very significant increase in the data available for modeling. Now, previously we developed a model, which I'm referring to here as the process original, which basically involved prior selection of variables based on existing understandings of erosion process relationships and then fitting it with limited data available at the time. And so the plot you can see here just shows how some of these relationships vary as a function of, say, sinuosity or percent silt clay in the erodible material, or the confinement of the reach and how that might affect channel erosion. So the submodels we ultimately compared involved the original process model, then the same model, but using the updated channel change data. And then alongside more data-driven methods such as the general additive model, which with automated variable selection and allowing nonlinear relationships, and finally a random forest model, so machine learning algorithm, automated variable selection, view constraints. And then we tested these models using a technique called cross-validation, where we basically divide the data randomly into a subset for model fitting and then a subset independently for testing, and we repeat that many times over to assess predictive performance. So the results of this analysis highlighted that ultimately the random forest model had the least error, both in terms of fitting, but also in terms of predictive performance and cross-validation when you were independently assessing the model. And for that reason, we decided to focus obviously on the random forest when it came to predicting that lateral movement rate or the migration rate of riverbanks at the reach scale. But that's only part of this story for riverbank erosion. We also needed to estimate the bank heights, and we developed an algorithm to basically do that from the LiDAR DM. And as you can see here, it's a considerable improvement on what was used previously, which was a very simple equation relating bank height to mean flow. This now tries to extract that information directly from the LiDAR, and we see considerable improvement relative to the data available for assessing our predictions. So having updated the bank height estimation, we then were able to recompute the net bank load using the random forest model that had been fitted, and we ended up with about 1 million tonnes per year from net bank erosion, which is an increase from 0.7 million tonnes on the previous model. Now, in terms of summarizing, I've focused on the landslide and riverbank erosion components because that's where we made the most changes. But as I mentioned, we also made some changes to the superficial erosion and floodplain components. But overall, we do see a significant increase in terms of the amount of sediment delivered to the stream network with the updated model. So it's gone from about 7.5 million tonnes to 8.5 million tonnes with the updated modeling. But the proportions coming from different erosion sources are quite consistent, actually. You'll see a slight change there for gully earth load, but that just reflects the update in land cover data between the earlier and the updated model. Whereas the other components obviously reflect both some influence from land cover, but also significant changes to the submodels involved. Now, those numbers obviously give you a kind of an overview regionally, but part of this upgrade involves producing high resolution spatial predictions, and some examples of those are shown here. The shallow landslide erosion map, which I shared earlier, but also a spatial representation of the sediment yield from surface erosion. So this is the sediment yield to the stream network from overland flow and raindrop erosion, as well as the riverbank erosion prediction shown here on the right. Now, in addition to those erosion process specific predictions, we've also got outputs related to the accumulated net suspended sediment loads in rivers, as well as the total suspended sediment yield per stream segment watershed, giving you, I suppose, a spatial depiction of the combined contribution of different erosion processes to the sediment yield at the watershed, that sub-watershed scale. We did compare modeled versus stream gauging estimates of suspended sediment load. The data is very limited, so that is quite challenging. But we did see an increase in the correlation between the measured and modeled, which is good to observe. So just to wrap up with some key messages, look, hopefully you can see there are considerable benefits from using high-resolution LiDAR-derived DEMs in erosion modeling. Clearly, examples of that include improvements in model parameterization and performance due to the more accurate topographic data. So landslide susceptibility modeling was a particularly good example of that. The better representation of the stream network, in particular that channel sinuosity or channel slope, these are key variables for bank erosion modeling, as well as the production of high-resolution raster layers. And in particular, this shallow landslide susceptibility modeling has allowed us to produce high-resolution, accurate layers that can be used to better target tree planting to the most susceptible land. Whilst the LiDAR-based SedNet model has improved the spatial predictions of erosion process contributions to suspended sediment loads, and now allowing us to share higher-resolution layers to support land and water planning. And I suppose now that we've developed this LiDAR-based model, there's opportunities, of course, to undertake scenario-based modeling using the new model to look at erosion mitigation or climate change scenarios and how they affect suspended sediment loads in the future. So that concludes my presentation. Obviously, I'd be happy to take any questions. Flo might be handling that, so.
Kia ora. Yes, thank you so much for your awesome presentation, Hugh. There's 2 questions in the chat from Nina. I'll start with the second one, because I think you might have partly at least answered the first one. So the second one is, how often would you want new LiDAR data to update models and predictions? Would you be able to comment on that?
We don't actually need new LiDAR update data. So essentially the model uses the LiDAR information to represent the topography and then uses the data we've collected to parameterize the submodels, and it makes a prediction based on that topography. So although there are changes obviously as a function of landsliding and riverbank erosion, they're relatively small compared to the overall shape of the landscape. So I don't see that as a requirement at all. Ultimately, the modeling we do from here on is scenario driven. Having set up the model, and this could be done for other regions which have LiDAR coverage, the questions then are more what do we want to know? So it's things like what are the balance of erosion control strategies versus impacts of future climate change on storminess, and how does that affect? What's the net effect of that on, say, future suspended sediment loads? So it's getting a better understanding of the balance of, say, land use change, erosion mitigations, and the future effects of climate. So we see the modeling, or what modeling we've done here, and the development side of it is around setting up the model, providing a baseline, and then being able to use that to answer future questions.